This is Math 251, section 14.2. The topic in this section is line integrals. I'm going to warn you in advance, this is a pretty long section. If you get through this section in this chapter, the rest of it is a bit quicker. So hang in there, and we will get through this one. All right, so in order to introduce the concept of line integrals, we're actually going to look at two distinctly different types, but really kind of it'll be subdivided into three. The first one is called a scalar line integral. And in order to begin the discussion of what a line integral is, I would like to remind you of some of the integrations that we've been doing. First of all, in Calc 1 and Calc 2, you integrated functions over line segments. When you had an integral that looked typically like this, you were integrating over the line segment from A to B. Typically think of that as being the x-axis. In this class, we've integrated both double integrals over regions and also triple integrals over solids. To integrate a function over a region R, we looked at a function of two variables, and we had to integrate dA, where the region R was some sort of a two-dimensional region. And then most recently, we've integrated over solids. We usually called them D. A function of three variables, f of x, y, and z, dv. Where our three-dimensional solid maybe looks something like this. All right, so we've integrated over line segments, regions, and solids. You might notice that with both the regions and the solids, we went from, for example, a rectangular region with all straight sides to a curved region. And again, with the solids, we allow for curved pieces, right? The only thing we haven't allowed to curve yet was all the way back here to the original, the line segment. We only allowed straight line segments, not curved ones. So perhaps a natural question to ask at this point is it possible to integrate a function over a curve? Well, fortunately, the answer is yes, or unfortunately, I guess, depending on how you see it, because it's more math to learn, but it turns out to be some pretty useful math. So that's where we're going with the concept of a line integral. I know it seems weird we call it a line integral when we're integrating over a curve, but it's just one of those things you got to deal with. So the goal is to integrate over a curve C, and we know that curves are often written as vector-valued functions, so we'll consider our curve to be some function r of t. So if that's my curve C, defined by the vector value function r of t, just like with the straight lines, we're only integrating over a portion of that curve, so we'll designate the endpoints as t equal to a and t equal to b. What happens when I integrate a function, f of x and y, over this curve, C? I'm going to actually leave the differential off for right now. I'd like to look at the geometry together first, and then once we've done that, we'll kind of figure out what has to go here. Right? So, thinking about the geometry again, I'm now integrating f of x and y. Z equals f of x and y is some surface. So I'm just going to kind of create a generic surface here. And I'm integrating along this curve C, but C was in the xy plane. So C is down here somewhere. Again, from t equal a to t equal b. Imagine, if you will, taking this curve and projecting it up so that you can see its projection onto this curved surface. So perhaps here, above t equals a, maybe we hit the surface there. And maybe here at t equal b, we hit our surface there. And we're going to have that same curve, but in some sort of a slanted way, following along that surface. If you imagine taking every point on C and following it up to its point on the surface, the corresponding point on the surface, what you end up getting is kind of this wavy curtain here. And what we're actually finding when we do this integral is the area of that wavy curtain. All right, let's talk then about what the differential should be. I'm going to take one specific little piece in here. And since it's a piece of a curve, it's going to have to be a ds. Right? Not a dx, which would be a piece of a straight line, but a ds, which is a piece of a curve. And if I follow that little piece up to its corresponding piece up here, and if I multiply the height, f of x and y, times the ds, the base, I've got the area of that rectangle. And again, as I shrink the ds down infinitesimally small, I'll be able to actually accommodate the fact that it's not truly a rectangle, but a curved surface that I have here. So the differential that applies here is ds. True, because we came with this little piece of a curve, but also unfortunate, because we all know that the integrating ds is not usually what we want to do. Usually we want to integrate dt, because our curves are usually parameterized with respect to t and not s. Fortunately, there's things that we can do. First of all, since c is equal to r of t, I know a couple of things. Right? I know, first of all, that this could be written as, let's write in vector form, x of t, y of t. And so the x and the y and the f could actually be changed for x of t and y of t, making this a function of t. So that's not going to be really a problem. This piece will be easy to deal with. As far as the ds piece, just a reminder that ds dt actually represents the speed. Right? S is the arc length of the curve, so the derivative of that arc length or distance would be speed. But we know another way to write speed. Speed can also be written as the magnitude of the velocity vector, r prime. So ds could be written as the magnitude of r prime multiplied by that dt. So, if I put those two pieces together, the fact that x and y can easily be changed into functions of t, and the fact that ds is the magnitude of r prime dt, I can change my integral into the form f of, I'm thinking of x and y now as functions of t, times ds, which is the magnitude of r prime of t, prime of t, dt. And now that we're going with respect to t, we'll integrate between those endpoints, t equals a and t equal b. So, When you're faced with finding a line integral over a curve, the trick is going to be to look at the parameterization of the curve, an r of t form, change your f into its t form, and multiply by the magnitude of r prime. That's summarized for us at the top of the next page in the box, right there. And then we've got some examples to work with. So, in our first problem, we're asked to integrate the function xy to the 1/3 power, ds. So there we have it, a line integral, scalar line integral, where c is the curve y equals x squared for x going from 0 to 1. So we're actually integrating. There's that piece of a parabola, y equals x squared, from x equals 0 to x equals 1, which would mean that y would also be 0 squared or 0, and 1 squared is 1. Let's start by parameterizing our curve. We know here that r, simplest parameterization is just to let x be t, and y therefore would be t squared. So r would be t, comma t squared. That means the derivative, r prime, would be 1, comma 2t. I wrote it out separately here, although you may not always do that. So just to point out, as soon as you defined your r, you've defined your x and your y. All right, I'm now going to use this. I'm going to say what I really need to do is to take my f of x of t, y of t, and multiply by the magnitude of r prime dt. And let's see, here's my function f. I'm going to go ahead and plug in the x is t and the y is t squared. So that's going to become x is t times y is t squared, all to the 1/3 power. Then I'm going to put in the magnitude of this r prime, dt. And since x was equal to t and x goes from 0 to 1, that means t is also going to go from 0 to 1. All right, a little bit of algebra here. That's t cubed to the 1/3 power, which would just be t. And the magnitude of that vector would be the square root of the sum 1 squared plus 2t squared. So I end up with the integral of t times the square root of 1 plus 4t squared dt. That's actually not difficult to do by hand, just a simple u substitution, but just to save some time, I did do that in the calculator, and I ended up with about 0.848. All right, so there's our first example of a scalar line integral. Let's do, let's do a couple more, I guess. In number 2, we're supposed to integrate the function x plus y ds. It says over the path shown, and I actually neglected to put the path into your copies, so we'll go ahead and create our own path here. I would like the path to look like this. It's going to start at the origin, and in a straight line we're going to go to 2, 2. And then in another straight line we're going to come down to 4, 0 and stop. All right. In a situation like this, where you can't define the path by a single equation, your best bet is to do it in two pieces. So I'm going to say this part of the path I'll call A, and that part of the path I'll call B. And we'll have to do two separate line integrals and add them up. So for A, we really have the path y equals x here. All right, let's parameterize our path. We need an r, just like we got over here. So if I let x equal t, then y is also going to be t. And that means r is just t comma t. And I probably should start putting my intervals in here. Since x is t and x goes from 0 to 2, t will also go from 0 to 2. We know we're going to need r prime, so let me just write it down here. That would be 1, 1. So my integral goes from 0 to 2. I have x plus y, so that would be t plus t, times the magnitude of r prime, square root of 1 squared plus 1 squared, dt. That's going to be 2t times the square root of 2 dt. And let's just run through this one. It's pretty simple and it gives me an exact answer. I'll have t squared square root of 2 from 0 to 2, which gives me 4 times the square root of 2 for A here. All right, let's also look at path B. Let's see. This one is got a slope of -1, so y would equal -1x. And if you can just kind of use your imagination, if I were to go up here, the y-intercept, it would actually cross at y equals 4. So y equals -1x plus 4. Once again, I'm going to let x equal t. And so y is going to be minus t plus 4. So my vector r, t, comma minus t plus 4. X is t, and x goes from 2 to 4, therefore t also goes from 2 to 4. I know I'm going to need r prime, so let's do that. That's going to be 1, -1. All right, so setting up my integral, 2 to 4. Again, the integrand is x plus y, which this time is t, plus the opposite of t plus 4, times the magnitude of r prime, square root of 1 squared plus -1 squared, dt. When I go to integrate that, this square root of 2, well, actually, let's just do it this way. T is clearly add up to 0, so I've got 4 times that square root of 2. And once again, I'm just going to go ahead and integrate that by hand. It's not very lengthy. Gives me 4 square root 2 times, times t, almost forgot the most important part, from 2 to 4, which would be 16 square root t minus 8 square root 2, square root 2 is 8 square root 2. So, altogether, if I add up my two pieces, my final answer then would be 12 times the square root of 2. All right, I know this is just a little bit lengthy, but let's go ahead and finish. There's only one more example of scalar line integrals. I'm going to go ahead and finish that with you right now. In example 3, we have a slightly different application. We're asked to find the mass of a thin wire between those 2 points. Since we're not given any additional information, I'm going to make the assumption that this is a straight line. Probably should have stated that, but we'll assume it here. And my density function is given by xy divided by z. All right, to find that mass, I'm once again going to use the concept of a line integral, a scalar line integral. The mass is going to be the integral over that curve C, it's really a straight line segment, of the density function, ds. So, what I actually want here is the integral of the density function xy divided by z, integrated along that specific path between those 2 points. All right, we know how to find a vector-valued function for a line between 2 points in 2 or 3 space for that matter. We know we need a direction vector. So to get r, my direction vector, I'll just subtract the 2 points, terminal minus initial. That's going to give me 2, 2, 2. I'll use the first point into a vector, gives me OP, 1, 4, 1. And that means that r is t times the direction vector plus the point vector. Or in this case, 2t plus 1, 2t plus 4, 2t plus 1. Okay, just finding the equation of a line. By the way, I could have used the vector 1, 1, 1 here. I could have divided it by 2 because we know that would still be in the same direction. But because I didn't, because I left it in its original form, I know for sure that I go from this point to that one when t goes from 0 to 1. Sneak that in there. All right, I'm going to need r prime, which is 2, 2, 2. And now I'm ready to plug everything in to my integral. We are going from 0 to 1. Remember, r defines the x, the y, and the z. So x is 2t plus 1. Y is 2t plus 4, divided by z, which is 2t plus 1. ds, just as a reminder, is the magnitude of r prime dt. So that would be the square root of 2 squared plus 2 squared plus 2 squared dt. And I got lucky this time. I can divide out the 2t plus 1, so that just simplifies to 2t plus 4. That's the square root of 4 plus 4 plus 4, or the square root of 12. And once again, I'm going to go ahead and just quickly get a nice exact answer since it's not too difficult. That integral, I'm going to pull the square root of 12 out, and I'll get t squared plus 4t, evaluated from 0 to 1, which is the square root of 12 times 1 plus 4 minus 0, or 5 times the square root of 12. And they didn't give me any units, but this is a mass, so this would be like grams or something like that. I guess I could rationalize, I could pull that out a little bit, and be 10 square root 3 grams, or whatever mass units we happen to be using. All right, so that brings us to the end of the first type of line integral we're going to talk about, the scalar line integral. We'll continue in the next video.